Imagine tracking the motion of a sports car. It cruises at a steady pace, and then the driver slams the accelerator. Calculating the average acceleration for that entire run yields a single static number. But that number is a mathematical blur. It obscures the actual changes in performance occurring within that time interval. In the physical world, thrust curves shift as gears change. Atmospheric drag compounds as velocity increases. The rate of acceleration remains in a constant flux. Yet early physics education conditions us to ignore this. We solve problems assuming acceleration is a perfectly flat, uniform constant, an idealized state that rarely exists outside a vacuum. When variables like air resistance or changing engine power are introduced, basic algebra collapses. To solve advanced kinematics, we must adopt the native language of motion, calculus. True mastery of mechanics requires analyzing a system's exact physical state at an infinitesimally small moment in time, rather than relying on a macroscopic average. Left, standard algebra, like v equals u plus at. Right, the differential definition, velocity as the first derivative of position. Applying algebra to variable acceleration is a trap. When acceleration fluctuates, v equals u plus at shatters, yielding impossible results. The moment a problem defines acceleration as a changing function of time or position, differentiation and integration become the only valid mathematical tools. Relying on algebraic shortcuts for a variable state is like trying to map a dynamic, curving coastline with a straight wooden plank. You lose the actual shape of the motion. At the bedrock of all mechanics are two base entities, position in space and the progression of time. Everything else is derived from their relationship. We can visualize this hierarchy using a vertical stack of 3 coordinate graphs. Looking at the top position time graph, instantaneous velocity is the first derivative, the exact slope of the tangent line at any single point on the curve. As the slope of that position curve changes, those numerical values drop down to dictate the exact height of the velocity time graph. The cascade continues. Instantaneous acceleration is the first derivative of velocity with respect to time. We are now tracking the slope of this middle curve. The slope of the velocity curve projects downward to draw the acceleration graph at the bottom. Because velocity derives from position and acceleration derives from velocity, acceleration is the second derivative of position, or d squared x over dt squared. This third graph tracks the precise evolution of velocity, defining acceleration as the mathematical curvature of the object's original path through space. This hierarchy clarifies a major conceptual hurdle, the belief that if an object's velocity hits zero, its acceleration must also vanish. Consider a ball thrown vertically. At its exact peak, the velocity vector shrinks to zero, but the acceleration vector, driven by gravity, remains constant at 9.8 meters per second squared downward. Acceleration is defined by the change in the system's state. It operates independently of whatever the current velocity happens to be. A second trap involves the interpretation of negative signs. A negative acceleration value does not automatically mean the object is slowing down. If velocity and acceleration have opposite signs, the object slows. But if both share a negative sign, the object speeds up in the negative direction. Misinterpreting these vector signs is a primary reason students struggle to solve advanced problems, as they fail to correctly translate the physical direction into the math. Linking motion through time is standard, but how do we solve a system where acceleration is provided as a function of position, a of